This meeting is being recorded. Okay.
I'm going to stop my video so I'm not showing up on the screen, okay?
Okay.
Our Dean, you're good to go whenever you're ready.
Okay, thank you. Good afternoon. Welcome to our second Zoom lecture of the season. I'm Ardeen Nelson. I'm chair of the steering committee this year. And for those of you that don't know me, I wanted to say a few things before we get started today. Notices have been going out. There's been some issues with some emails, and there is a notice on the website that says if you're using a non-OSU email address, to send it to me at nelson.13. We're trying to collect all those so that proper emails will get to everyone, even if you're not using the current mail system at OSU. If you have friends that recently retired and became emeritus, the new members deadline for application is October 12th. That information is all up on the Academy website. And what just came out is about the Emeritus Academy small grants. The deadline for those are going to be November 6th. There is new information on the website and a new application procedure to go through so we can collect those. And I think that's all I really have to tell you here before we get started. Today, our lecturer is Jean-Michel. I'm laughing because I've told you folks this before, I'm very bad at foreign language. And so please forgive this. But Jean-Michel Guldmann, he's Professor Emeritus of City and Regional Planning at the Knowlton School of Architecture, where he taught from 1977 to 2012. He served as the Knowlton Interim Director from 2005 to 2007. He has a master's in industrial and system engineering from School of Mines in Nancy, France, and a PhD from urban regional planning from the Israeli Institute of Technology in Haifa, Israel. He's taught courses on optimization, decision analysis, population economic forecasting, and energy and regional modeling. He has supervised to successful completion the dissertations of 31 PhD students, including 6 since his retirement in 2012. He has also hosted and mentored 6 visiting scholars from China and Turkey. His current research focuses on the analysis and modeling of urban heat islands and its mitigation and role of green infrastructure in urban sustainability, air pollution from transportation and other sources, and urban energy consumption. His research methodologies include spatial economics, simulation and optimization with an input big geospatial data, LIDAR, remote sensing, Celsius, and CADSTR. He has published a book entitled Industrial Locations and Air Quality Control, a Planning Approach. He has also authored 95 peer-reviewed journal articles and 2 book chapters. I'm really excited to see this presentation today, and I'm using my fake background of grass because we need clean air. And I'd like to welcome Jean-Michel.
Thank you. Okay, so you know already the title of my presentation. This presentation is kind of the outcome of a long stream of research that has involved several PhD students and visiting scholars, and I want to immediately give them credit. So first of all, PhD graduates from City and Regional Planning at OSU, Kim Jun-pil in 2009, Chun Boom-seok 2011, and most recently Park Eugene in 2020. And this collaboration and advising and mentoring will be reported in this presentation, and you will see the progression of the research from something that I wouldn't call primitive, but rather simple, to more and more sophisticated. And of course, the credit has to be given to these wonderful PhD students. In addition, I had a visiting scholar, a wonderful visiting scholar from China, from the Chinese Academy of Science, who was here for 1 year, but we were able to write 2 papers, and we continue today an active collaboration. So let me talk a little bit first about urban heat island basics, what you should know, although you probably know it already. And then I will talk a little bit about the different pieces of research and how they kind of are interlinked and what are the insights that they provide. So the urban heat island is not something totally new. In fact, in the 50s, 60s, there were already researchers who had noticed this phenomenon. And basically, the urban heat island is characterized as an increase in temperature in built-up areas of cities, and in contrast to the temperatures in the rural areas that surround the cities. And converting soil and vegetation into impervious surfaces is a major cause, because materials and impervious surfaces capture solar thermal energy and re-emit it and increase the temperature. And also solar energy is absorbed in the walls of building, and that increases the temperature in the air surrounding the walls. On the other side, vegetation areas have lower temperature because they re-emit less thermal energy, because they use part of that thermal energy for evapotranspiration. And of course, trees block solar radiation, provide shading. In addition, in urban areas, particularly in areas of high-rise buildings, you have what are called urban canyons, and they affect air circulation, wind flow, thermal energy absorption. And why is this important? Well, it is important because in 2007, the United Nations indicated that more than 1.5 billion people lived in urban areas worldwide, and forecast that 60% of this population will live in urban region in the future. I think I cannot see the date here, but it's the target time is 2030, so it's quite soon. Okay, so so that's a little bit the background, and you can see on this diagram a summary of all the factors that create the urban heat island. Of course, the sun, and then you have, high rises and smaller buildings. You have water. Water is an element that reduces temperature. You have grass, you have trees. All these things interact to create this phenomenon in a fairly complex way. And this is kind of an iconic diagram that shows the profile of temperature across the city with a peak at the center, but you can see secondary peaks, for instance, in highly built up suburban areas and so on. So it's not only one place, it can be different places within urban areas. this is also an iconic picture. Some of you may know it. It's the rooftop of Chicago City Hall. And this is a building that has had green roofs partly. So you can see where here in this area we have little bushes and grass and so on. And on the right, you can see an infrared picture that shows you the temperature. And you can see that the areas that are covered by grass, for instance here, are on the lower end of the temperature scale. This is a Fahrenheit temperature scale, around 74 and so on. The top one, this rooftop, go up to 151 degrees Fahrenheit. So this shows you the tremendous range of temperature that can be created in urban area where you have or not vegetation. Finally, just a small point. Of course, much of essentially all the studies I will present involve what we call land surface temperature at ground level. Why? Because essentially we use satellite information, and satellites capture the temperature at ground level. But of course, we are not ants and we are not living at ground level, but there is a very close correlation between what we call air temperature and land surface temperature. And here, I'm just showing a diagram of some data in Beijing that shows the close correlation between the two. So this simply suggests that we can use a land surface temperature, and this has been verified by many researchers. Okay, so given this background information, what is the overarching research goal that underlines this stream of research? Essentially, to improve our quantitative understanding of the relationship between land use, urban land use morphology pattern, and the UHI, using first remotely sensed data and second statistical analysis models. Why? Because if we understand the relationship between temperature and the way we organize cities and neighborhoods and so on, we would be able to assess the consequences of different actions, urban actions, both locally and citywide. And of course, that will be more and more important in the future, with global warming essentially lifting up the temperature curve that I showed you earlier over time. And so that would reduce energy consumption, would improve air quality, because high temperature help generate more ozone and other pollutants, would reduce heat stress on the population, and overall improve public health. So there are quite a few reasons why we want to fully understand this relationship. So let's start first with a first stream of research, which I call land use planning and UHI, based on the work of my first PhD student in this stream of research, Jean-Michel Guldmann, and that was published in Environment and Planning in 2014. So this research, which I call a little bit primitive, though it's really not technically primitive at all, used only Landsat 5 data. Landsat is a satellite, 5, it's one generation of satellite, and it produces information for every 30-meter square cell on the ground. And you can see here, the location here is Columbus, and you can see that it's part of this path and location. And from this information, we derive land use, we derive remotely sensed temperature, and we derive what we call NDVI. It's an index of vegetation. So I'm going just to illustrate that information. Here you can see, it was in 2005, the pattern of surface temperature in Columbus metropolitan area at large. So of course you can see Columbus itself, but you can see satellite cities, Marysville, Delaware, probably Newark, and so on. And you can see the redder, the higher the temperature, the bluer, the lower the temperature. So remember that information is available for every 30-meter square cells that cover the whole area. Likewise, using satellite information, we can generate land use patterns. So you can see here the 6 patterns of land use, including water, agriculture, cropland areas, green areas, which would be trees and grass, residential area, impervious areas, and urban areas. Mostly, also impervious, but probably a lot of buildings. So, in addition, we can derive from satellite information what we call the NDVI. It is a vegetation index that varies between -1 and +1. When it's less than 0.2, it means really there is very little or no vegetation. It's mostly either water, urban, or bare soil. Between 0.2 and 0.5, it's kind of mixed vegetation within residential areas. We have a lot of that in Columbus. And when the NDVI is greater than 0.5, we have really areas fully vegetated like forest. So without going into technical detail, the idea here is to try to explain the temperature in the red cell that you see here as a function of the land use patterns that are all around. So this we call a buffer. And you see, for instance, one type of land use, let's assume that it's grass, here is in green, but we may have others. We may have buildings, we may have water. And so the idea is to build a statistical relationship between the temperature at that cell, the central cell, and the land use pattern all around. And just to give you an example, I just took this table. I promised myself I wouldn't show you too many tables, and I won't. But here it's an example where we explain the temperature of a cell, which could be water or agriculture or green or residential and so on, as a function of the surrounding pattern, all measured in NDVI. And you can see here the R-square obtained. They are fairly good, and all the signs make sense. And we used both NDVI and area, and you can see that here the simple model is just to try to explain the temperature of a given cell, a given location, by the NDVI at that location. And that doesn't work very well, very low R-square, whereas when we introduce what is surrounding that cell in the buffer, we improve. But for instance, impervious and urban areas are better measured are better explained by area measure, whereas others by NDVI measure. And if we take both of them, we even improve more the explanation pattern. We still do not do that well, as you can see by the R-square. When the R-square is 1, you explain everything. So impervious and urban areas are still not well explained. And that was one of the reasons why the reviewers of this piece of research told us, well, you cannot really apply your method to the center of Columbus. So we took out the center of Columbus and we left it for further research to account really for the complexity of urban structure. So having such a function, what we did was to use the relationship to test what would happen if we insert green spaces around urban areas. So this is an area around the Tattle Crossing area. So it's primarily, shopping area with a little bit of residential areas and some green areas on the surrounding. But what you can see here in blue is urban areas. I think it's mostly commercial buildings and surrounded by what we would call impervious areas and probably mostly parking lots. So this was the baseline where you have the temperature of these different activities as observed from satellite information. And in the diagram below, we've inserted a kind of green belt around the blue area. And what you can see is on the diagram below are the resulting temperature. And without going into detail, what we can compute is after inserting this green space belt, the temperature, the average temperature for the whole area would go down from 35.62 degrees Celsius to 30 degrees Celsius. So more than 5.5 degrees Celsius. So as an example of what it would do if we would just throw away all the parking spaces and replace them by a little forest. Of course, that would be a problem for people to go to shopping, but maybe that's no longer a problem online. All right, so that's a first example of application of this kind of model where you can test various actions. And here it's hypothetical, of course, it's very hypothetical. It's for illustration purposes. You can test, various land use actions. All right, so this was the first part of the research, and here that table kind of shows different level of vegetation in this green belt and the resulting change in temperature. I'm not going to spend too much time on this. All right, so as I said before, we didn't deal with the center of Columbus. So that, in fact, became the subject of research of my second PhD student in this stream, Boom-Seok Chun, the Columbus urban core. And that will lead to different techniques because we need to represent the 3 dimensions of the urban core. And so just to summarize very quickly the approach, we develop a digital 3D city model with LiDAR data, compute various parameters, use urban temperatures from satellites, combine all this information, apply to the center of Columbus, and estimate statistical model. So here is the area of study. I'm sure you recognize it, right? The Scioto River, here Scioto, here the Olentangy. And you can see here the limits of the area. And that area involved about close to 40,000 building footprints. So this is very important here. We obtained the building footprints from the Franklin County auditors database, where they have the footprint on a GIS framework for all the buildings everywhere. So we had that, and we wanted to rebuild the city, but of course electronically. We are not going to rebuild anything practically. So just for those who may not know, what we use for that is called LiDAR data. Essentially, look at this plane. It sends laser pulses, and these laser pulses hit surfaces or buildings or trees, and then they bounce back. And using the time of bouncing back that goes very, very quickly, it is possible to measure the height of the point that was hit by the laser pulse. So that is a very, very useful piece of information. It is available publicly. The city of Columbus has conducted a lot of data gathering, though they are not using it very much, but it is available, and we've used it also for the last piece of research. So I'm going to try to just outline how we do recreate a city. So here you can see all the dots are the LiDAR points. And you can see here the footprints. So what you do is you take all the points within a footprint and take the highest one. Assumedly, these would be the ones hitting the roof. So you average them, that gives you an estimate of the height of the building, and you have on the right a recreation of these buildings. So this was done for all the 39,000 buildings, here you can see a little bit more detail of a more complex form. And here is what is recreated. And here is just a view of downtown Columbus with different buildings. I'm sure you can recognize some of them. So that was a first piece of information that we had to do to compute a lot of variables. For instance, having the rooftop areas of all the buildings, but also morphology variables and solar insolation variables. So I'm going to talk about that. One important piece of information is called the sky view factors. Here, you measure at the ground level how much of the sky you see. And that can be computed, you know, with, of course, everything is done with the computer. There are no hand calculation. If there is no obstruction to your view of the sky, you can see the sky in every direction. Let's say you are in the countryside in an agricultural field, the sky view factor is equal to 1. If it's nearly all covered and you can't see the sky view factor is 0. So it varies between 0 and 1. And you can see here what we call fish eye lens of different views. Here is the countryside, townhouses, multifamily houses. And here, this is in Manhattan, New York. So that's the idea of, you can see here that the sky view factor will be smaller than here. Here it's at its maximum 1. And you can see the pattern of sky view factors. You see that they vary in, from 0 to 1. And in red, you see these areas, it's close to 1. And the green and yellows are lower. That's the more built up area. Another calculation that must be done is solar radiation. So this is done, by the way, with the software ArcGIS. So that's very nice. You don't have to design your own software. And essentially, it does something similar to the sky view factor. At any given point at ground level or on a roof, you check how much of the sky you see. So let's say this is what we call the view shed. And then you look at the path of the sun on the day you are doing the analysis, and it will tell you how much solar radiation will fall on that location. In addition, you look at diffuse solar radiation. When there is no sun, there are still solar radiation, and then you combine them. So with all that, you have a measure at every point at ground level or on rooftop of the amount of sun that reaches that point. And you can see here some of the data. That's the temperature data, all right? And here we know we have all the high-rise building downtown. That's the NDVI, the higher toward the red, the more vegetation. So obviously we don't have much here. These are the building footprints, and this is the map of solar radiation. So this information is available for the whole area. And the next step is really to capture that information within grids. So here you have, for instance, a 30-meter grid, here a 480-meter grid, and here, for instance, we would capture what you see here are the rooftops of buildings downtown. So we would measure how much of a rooftop is in a cell. For instance, here it's 100%, but here it's less, and here there is nothing. So we can capture all that information, and all this is done with a GIS. And we overlap all this information, so we create a large database with several information and for different cell size. And of course, the more detailed, you see, the smaller the cell size, that's 120 meters, the more detailed, 240 meters, 480 meters, it becomes less precise, of course, but if it's less precise, the computations are quicker, so there is always a trade-off between precision and computation time. Okay. So what we used is simply what is called regression analysis. It's to relate the land surface temperature in each cell to 5 variables. Building ground floor area, which is really building rooftop, solar radiation, sky view factor, NDVI, and water. And we found out that, in fact, water has quite a significant effect. Now, this first model, I apologize to those who probably don't like too much statistics, but just to explain the relationship, we tried to estimate these coefficients A0, A1, A2, etc., by looking at the data. But because there are interactions over space, and particularly because air is not at a standstill and air moves, there are interactions between cells, between neighboring cells. That's why one uses now much more what is called spatial models. And here is an example where we account for the effects of neighboring cells. So that's what I wanted just to say. And just very quickly, and we can look at, let's say, this coefficient for 480 meters, you can see that, for instance, building rooftop, the coefficient is positive. We would expect the more rooftop, the higher the temperature. The more solar radiation, it's also positive. The higher the temperature. SVF, the higher SVF, the lower the temperature, because air can circulate. Same thing with NDVI, negative. The more vegetation, the lesser the temperature. And here, water, the more water, the lesser the temperature. So the results turned out to be very consistent with theory and had the expected magnitude. And most importantly, in statistical analysis, they were all very significant. And you can look at their corresponding t-value, if you would like. So what do we do with that? We've done an estimation. Well, we did now a study, a simulation study downtown in Columbus. So we took this area, it's a sub area, and you can see the green parts, if you can see them, are parking lots that we decided to green by putting vegetation, trees and grass. It would be measured in terms of NDVI. And the red part are rooftops, which we would also green. So you can see here a more detailed pattern. And you have here, you know, the numbers represent the building. And what you can see is, of course, 6 Greater Columbus conventions that exist, but city center roof was 8. Of course, remember, the study used data in 2005. At that time, the city center still existed. So we used the data at that time. Of course, if we were to redo that today, we would have to account for all the changes downtown. But in any case, this is an illustration. And what did we do? We said for all these parking lot and rooftops, we will green them. And the measure of greening is represented by the NDVI of that greening, 0.6, 0.8. So that's 2 scenarios. And the third scenario is to take all the other vegetated area, which are at least 0.4, and increase them by 25%. So then we used the model to measure the change in temperature. If you look at the scale here, you can see that they are all negative, which means they represent the change in temperature. And for instance, the darker spots like red or black are on top. You see -8, -7, -7, -6. So you can see the change in temperature. And of course, these effects kind of spread out even lightly because of the spatial factor. And here, of course, scenario 3 is the most proactive greening. You can see that changes in temperature are much more widespread. So in other words, the tool can help us make decisions in terms of where we put green spaces and what would be the effect. Now, it's not the end of the analysis. We should then use the temperature change to see who is less affected by the change in temperature or more affected, and what does it imply for energy consumption by the buildings in this area. that's something which is still on our research plate. But these are the results of that, and you can see the number of cells for each scenarios for different temperature changes. So here we've seen how to analyze a downtown area. I want to go fairly quickly over some work that was done with Xiaoxin Dai in Beijing, because they involved two things that were not accounted for: building shadows and parks explicitly. So a first study involved the Olympic area in Beijing, in the north of Beijing. And you can see here the pattern of temperature in this area. And you can see here the land pattern. This is the bird's nest. You see, so this is the primal Olympic area. But what they call the Olympic area is much, much larger and involves residential building, office buildings, all kinds of things. And in this little map, you can see black areas, and these are the shades projected by buildings, because as I told you, there are some quite a few high-rise in this area. So this is a very, very precise land use map, because it used data from a very recent Chinese satellite, I think it's called Gaofen, I think at the 1 meter detail. So that provides very detailed information on water, grass, trees. It distinguishes between grass and trees. And this is a progression as compared to previous research, where we used NDVI as a synthetic measure of vegetation without distinguishing building, their shade, road, bare land, and impervious surfaces, which would be mostly parking lots all the time. And you know, we used a similar type of models. And so without going into detail, essentially, we would see that water, grass, and tree would reduce temperature, so would shades, but building and impervious surfaces, which includes roads and other surfaces, would increase temperature. One interesting thing with this study, very quickly, is that, for instance, in the case of 90-meter grids, we were able to distinguish, to uncover some nonlinear effects between trees, grass, and water. So what you can see is that you have this declining curve, which simply measures kind of the decline in temperature, for instance, here for an increase in grass. But the way the temperature declines depends upon the amount of other land use in these 90-meter cells. So for instance, if there are 20% of trees and 20% of water, then the maximum amount of grass would go to 60%, and you can see the form of the curve, but the curves would be different. So that points to probably the need to pay attention to interaction between land use in terms of how local temperatures are generated. Another study that we did was on central Beijing, within the second road ring. Here you have the temperature pattern, and you can, for those who have been in Beijing, have all these lakes. And here is the land use pattern. So I think this is the Forbidden City, and south of it is Tiananmen Square. And so we had very, very detailed maps. You know, you can see the level of detail. So again, these data were used to conduct similar analysis. But one thing that was particularly interesting in the case of Beijing, as some of you may know, there are quite a few parks, small and some very large. And so here you can see the larger parks. And what we did was to build what we call a gravity index that would account for the effect of parks in terms of distance. Because when you are in a park, of course, the temperature would be lower, but the effect of a park, in fact, extends beyond the boundaries of the park. So here you can see the effect measured by this index. So These were, you know, the two extension of research within the setting of Beijing. All right, so now this brings me to the third part, the third and last part. I hope you are still with me. The role of building and tree shades. This research is based on the doctoral work of Eugene Park, who is now an assistant professor at Clemson University. Maybe she's attending this presentation, I don't know. But in any case, it involves really two important papers. The first one is to rebuild buildings in a much more detailed fashion. And the second one is this analysis of shades. Okay. So why focus on shade? Well, trees provide several services. First of all, they evaporate water and use energy that is not remaining at ground level. They provide shade, and of course, they block sunlight. And when they shade buildings, then the buildings are less reactive in terms of increasing temperature. And the third reason is really that the shade effect has not been well explored. There have been experimental studies of shading effect, and I had one visiting scholar who did that from South China University of Technology, but these are more experimental with one tree or two trees and a building and so on. But here we wanted to try to understand this effect at a larger scale. And so what was done in this stream of research was to develop within Columbus a complete 3D city model with buildings and trees and ground covers. And as you can see, this is different from the previous research with Bung-Seok Chun, where we could capture vegetation, but also only through the NDVI. And we would use here ArcGIS Pro to compute shadows and then measure the extent of these shadows on different surfaces, compute new variables, and come out with new relationships. So that's the last part of my presentation, which I'm going to present now. And here is the study area that I'm sure you will recognize, 315, 315, High Street, Graceland, 71, Bethel Road, Morse Road, and I think this is Henderson. So we go a little bit from 161 in the north to south of Henderson in the south. So that's the study area. So we purposefully took a kind of suburban, inner suburban type of area with a lot of variability, some commercial area here and elsewhere, residential, some forest, and so on and so forth. And of course, water. Here you have entry and the rivers. Okay, so here the step in this study were first to build this 3D city, but this is a much more elaborate 3D city than what we've done in the past, because we have building and tree objects, and we have to analyze the land cover in a great detail, then compute all these shadows, and then create variables, and then conduct the statistical analysis to explain the relationship between what I would call shade morphology and LST. Okay, so let me a little bit describe that. So here, what you can see is first the downtown building. I think that's the AEP building, if I remember. No, maybe not. Maybe that's nationwide. I don't remember. But in any case, here, in this earlier paper in Computer Environment Urban System, Eugene developed a machine learning procedure, random forest, to classify leader points, because using just the footprint, you can have points that fall at the wrong location. Some may be attached to the facade of the building, some may be on top of the building, some may be on top of a chimney on top of a building. In the case of residential area, they can be on top of trees. And therefore, if you just take the building footprints and take the LIDAR point, within it, you may make terrible mistakes in terms of estimating the height. So what was done was using this classification, machine learning classification, using a training set of buildings, a testing set, to develop the methodology, and with an accuracy of 96%. So that methodology was used by Eugene. I don't know how to use it, though I understand it, to essentially recreate all the buildings in the study areas that you have seen earlier. Then we had to analyze the ground level land use in details. Here are the basic categories: water, roadway, building, vegetation, other impervious, and tree canopies. Here are two satellite pictures, one without trees, it's off leaf, and here the same area on leaves. As you can see, this is Antrim, so here it's a part of Worthington. And so it was necessary to analyze this data also with machine learning type. We used an available commercial software called Feature Analyst to come up with all this information, doing the land use classification. Here, this diagram kind of outlines the process using various inputs to create the final land use map. So up to here, we have created all the buildings. We have analyzed and created the map at ground level. Now what we need to do is to rebuild trees. So this again required machine learning type of analysis. I'm not going to go into detail, but you use these remote sensing pictures and the LIDAR data to assess the height of the crown, to assess the area of the crown, and so on. And then there are some algorithm to decide whether the tree is isolated or is part of a forest. So all that is done to generate a pattern that is illustrated on this diagram, when you see buildings and you see trees. So these are actual trees in these areas. As you can see, of course, the assumption is flat tree. Of course, not all flat roof buildings, not all of them by far not, but are like that. But we had no choice. So you see here a driveway, and here the street, and so on and so forth. So this pattern was subject to what is called ArcGIS Pro to generate shadows. And here I'm going to show you for a given area, also in Worthington, the pattern of shadows generated from morning to the evening. So look well, here we are. You see the shadows which move from the west to the east. So we would have all this information. Now, the analysis has been done at a given hour, it's around noon, but you could do the analysis of shadows at any time in the day. I'll do it again just for you to recatch it, going from west to east when the sun rises from the east to the west. And the same area, without any tree, you can look at the extent of the shadows just of buildings on the ground and on other buildings. All right. So once you have these shadows, essentially you measure the shadows on the ground, on building facades, on building rooftops. And when it's on the ground, you can differentiate whether the shadow is on roads or is on other impervious surfaces or is on grass. So this provides us an extraordinary amount of detailed information, and the shadow analysis is done at the 2-meter level precision. So this is extremely precise. It takes, of course, a long time to simulate all these shadows, and it has to be done in pieces. You cannot just simulate the whole area in one shot. But here I'm pointing out, buildings and shadows. For instance, here, that facade B is exposed to the sun. Part of it is exposed to the sun, part of it is shadowed. The rooftop, part of it is exposed to the sun, part of it is shadowed. This side is completely shadowed. And in the background, this building shadows this building. So all that information is available. And you can see how it looks from top. And here, if you were to take out all the trees, you would see the shadows at ground level. So on one side, we obtain the temperature, again, from Landsat for 30-meter cell. And then we create all these variables for 39,000, close to 40,000 cells, all these variables like tree canopy area, tree canopy volume. For each such cell, building variables, total building envelope, shaded rooftop area, sun-exposed rooftop area, shaded illuminated facade areas, the other ones, shaded not illuminated facade areas, and ground level, vegetated ground, built up ground, water bodies, shaded vegetation, sun-exposed vegetation, and so on, sorry. Okay, so we have all these variables and we have the temperature, so we put them together in a statistical analysis. And here are the results. I don't present you a table, but essentially this model has an R-square of more than close to 0.99. And what is extremely interesting is that the effects and the sign are all correct, all as expected from theory. So you can see here the total building envelope has a positive effect. However, the part of the rooftop that is shaded has a negative effect. The part of the sun-facing facade that is shaded has a negative effect. Same for the other non-sun-facing facade, negative effect. Impervious area has a positive effect. However, the shaded part is negative. The other paved part is negative. The tree canopy volume, this turned out to be the most significant variable, has also a negative effect. And so is grass, but in a different way. When it's shaded, it has a stronger effect than non-shaded. And water bodies have also a negative effect. So what this tells us is that simply this model kind of really can account for the effects of land use, three-dimensional structures, and all shades. So that if you build or develop an area and you build and you plant trees and so on, you would be able, by running the ArcGIS Pro model, to compute the resulting estimated shadows and then estimate the resulting temperature. And that's what we did here on a small area. So this is a small area. You can see the building in red. And in blue, the blue dots represent existing trees, fairly small. And the yellow dots represent potential new tree location. So here is what we did. Here is the original area with an average temperature of 35 degrees Celsius. Then we simulated the growth of the existing trees to 80 feet high, 60 feet wide, a typical elm tree. And you can see then we computed the shades, then used the model, and find out that the temperature in this case would be reduced to 32.14 degrees Celsius. If we, in addition to this pattern, we plant 20 more trees in this area, it would be reduced by another 0.7 degrees Celsius. So this kind of illustrates how we could use the model. And of course, this is a small areas, but we could do it for the same areas that I showed you before or any hypothetical area. So this is simply what I wanted to tell you about this stream of research on the urban heat island. And thank you, and I'll be happy to try to answer any question you may have. Okay. Okay.
Unmute myself. Hi, I'm back on.
Okay.
And Thank you so much. Really enjoyed it. And it's really intriguing. And I wanted to say, what happens to all this then in the winter?
That's a very interesting point. And I didn't present that research because I wanted to reduce the overload, but I'm going to tell you, in the study of the center of Columbus, we did another study that was published in 2018 of looking at temperature every 2 months, and that included winter. And so what was very interesting, in November, I think it was in November or January, the effect of vegetation is to increase temperature, whereas in all the other months, it would be to decrease it, with the strongest increase in the summer. And the reason is simply that when you have a lot of vegetation in winter, it provides a protection effect. And that was something fairly new. And so that would suggest, for instance, that if you want to take advantage of vegetation in both the summer and the winter, what you would want is to have evergreen trees, because they would reduce temperature in the summer and they would increase temperature in the winter. So that's a part of the research that I didn't present because of time.
Do we have some other questions?
Yes, I have a question. And first, a comment to say that I noticed that we have 42 participants. It's almost like we're at the faculty club serving Buckeyes and cheese and other snacks. So that's really terrific that so many people are interested in your topic, Jean. My question to you is, where do you go next? What is the next question you want to answer with your research?
Yeah, we have Eugene Park and myself have kind of a research plan that started. We want to study the role of rooftop solar panels and essentially solar energy. So if you want to reduce global warming, you want to increase the use of solar energy, and at the endpoint, you would want to put solar panels on rooftops. But the problem is that, of course, if you have an area with a lot of vegetation, then a lot of rooftops may be shaded, and you would have to get rid of the trees to be able to put the panels. So there is, and so by let's say, assuming that you take out the trees, you reduce vegetation, you would increase the ambient temperature. So in a way, you would kind of negate the benefits of solar energy. So the issue is, what is the sweet point between having vegetation and having solar energy? And we are selected as sub areas in the area that I showed you to try to do this analysis and see how much area would be available for rooftops, and then increase vegetation or decrease vegetation, and do the computation and see, you know, what would be the resulting energy consumption and so on. So that's the research, the next step on that stream of research.
I also have a question, if I may. This is Bhavik Bakshi.
Yeah, hi, Bhavik.
Hi, haven't seen you in a while, so nice
That's
to,
true. That's true.
So, you know, I mean, interestingly, there is some work that we have been doing, and, you know, I'll send you an email for a longer conversation.
Okay.
You know, but the question that I have right now is, as far as, you know, trees are concerned,
yes,
you know, they certainly provide the urban heat island effect, you know, which is what you focused on, but there are also other aspects, other benefits that trees provide.
Sure.
For example, you know, the effect of shading could be on reducing the energy consumption in a house, you know, heating and cooling loads, for example.
Right.
You know, trees will also take up nitrogen and sulfur oxides and particulate matter and so on. So it seems, and there are some trade-offs here, right? If you do something to reduce urban heat island effect, you may help over there, but it may hurt in some other, ecosystem service, if you like.
Yeah.
Also, so I mean, really, what it seems is needed is an integrated approach that takes into account, multiple services,
Sure.
and also the design of the building and the surroundings and stuff like that. So, just want to know what your thoughts are on that. Have you been working on something like this? Do you know of other work of that type?
Well, I know of work on the role of vegetation in general, in terms of other ecosystem services. Of course, there is a whole area of ecosystem services. We have focused here specifically on outside temperature. And as I said just before, the effect of that outside temperature on energy consumption, for instance, in the summer, air conditioning is really, we haven't accounted for it, but this is part of the plan on solar energies. Of course, you would need to have models, even simplified models of energy consumption of buildings. And this energy could be provided by standard ways, let's say electricity or natural gas, could be provided by solar panels. And of course, you would reduce that energy by having more vegetation. So there is quite a bit of research also on energy consumption of building, accounting for all these environmental factors. And I hope to get more in depth on that. Regarding other ecosystem services, well, vegetation has mental welfare services. It's good for the population. A lot of research shows that areas with a lot of vegetation have positive effects on people, their health, problems of runoff, water runoff can be reduced with vegetation. You mentioned air pollution can be captured by vegetation, sure. So you have all these things, but remember that all these pieces of research are really based on just doctoral dissertations. So it's not that we had the possibility of doing an extremely wide research project.
Right. Okay. Thank you.
How about another question?
Hello, my name is Paula Meijerink. I'm a landscape architect and a professor in landscape architecture at the Knowlton School. Thank you very much for this talk.
Yeah.
My colleague Tamika Sims is here too. As designers, we are currently doing a design studio, a course at the Knowlton School on impervious surfaces. And in this particular one, specifically to changing the formation of these surfaces. What I'd like to seek your feedback on is, so in studying the relationship between trees and impervious surfaces, we all know the benefits, but we also see that canopy cover, we often see higher percentage of canopy cover in neighborhoods with higher education and lower canopy cover in neighborhoods with lower education, lower income. It would be interesting to see if maybe a racial distinction could also be drawn in relationship to canopy cover. And it seems to me that urban strategies need to be developed, how these, to create greater social equity in terms of canopy cover and the relationship to the city. Is this anything that your research, so the social side of urban heat islands?
It's really interesting that you ask this question, because another piece of research that was part of Eugene Park's dissertation was on the distribution of green space and their accessibility, equitable access. And I will send you that by email. It was published in a journal called Landscape and Urban Planning. where we did that for the whole metropolitan area in Columbus as well as in Atlanta. Here, to be honest, on this heat island analysis, we haven't done that because really a big effort had to be devoted to building all these big data set and conducting the analysis. But obviously, a downstream effort would be really to look at, you know, where are the higher temperatures, what are the population exposed to higher temperature. There was recently an article in the New York Times on a study with data on Richmond, Virginia, where they showed that a lot of red line districts, which were mostly inhabited by African-American population, had higher temperature and less vegetation than others. So and there are other articles in the literature that are focusing on these socioeconomic aspects. We are fully aware of that, but you know, we couldn't really get to do that at that point. But I'll try to email you one or two pieces on that if you're interested.
I would very much interested in that knowledge also because our school will be engaged in the Green New Deal Super Studio that's happening this year on initiative by the University of UPenn, Pennsylvania. Mm-hmm. It's late in the day, I'm stumbling over my words. So yes, I would very much appreciate that. My colleague Tamika Sims is also here, and I will post her address in the chat as well.
Okay.
This is a much more general question from a humanist. Can you hear me?
Sure, yes.
Okay. I'm from Detroit, where of course the so-called urban blight became so extreme that now community gardens are being planted in great numbers where entire zones of houses have been raised, which is in a sense the other side of thinking about zoning. That's an observation. My question actually is in relation to the third part of your talk about trees. My son is an arborist, and as a result, I've learned a lot. Elm trees, you know, are not being planted at all in this part of the country because the elm tree blight is so widespread. Trees that used to be planted frequently, like Bradford pears, which I have a whole screen of, are now officially declared a nuisance in Ohio and should not be planted anymore. So it's as if the whole notion of trees and the sort of green infrastructure is itself a kind of moving target. Do you see it as part of your social role to be in conversations with, you know, not only community organizing groups, but also, of course, landscapers and arborists who are responding to really quite drastic changes in our ecostructure at this time?
Yeah, I would love to interact with these people. You know, what we provide here is a tool that would help arborists and landscapers and so on if they say, well, we are going to plant in this area, these kind of trees of that side and so on. Mm-hmm. But what we say is, okay, well, we have here a tool that could assess the consequences of what you are doing. Mm-hmm. And then, you know, essentially you can decide what it is that you want, or decision makers, let's say policy maker, can decide. Yeah, that would be, you know, a natural outcome. As I said at the beginning in describing the overarching goal of the research, it's really, we need first to understand what is happening. Mm-hmm. Because just saying, yeah, vegetation is good, or trees are good, and this is bad, and so on, it doesn't really help. I mean, it's true, but what we want is really to measure the effect so that we can say, okay, here is the effect. We want to have this organization, this design, this is the result, and so on. And we can say that in advance so that you can make better decisions, better plans. But yeah, I would love to interact with arborists and landscapers, no problem. Thank you.
Thank you. Anyone else? No one is? Okay, so from a totally lay point of view, I end up with the feeling that when people talk about wind farms and solar farms away from cities, that maybe that's part of the long-term solution so that there's more greenery in cities to keep the temperature down. And I don't know.
It absolutely could be. You know, it could be that the conclusion is, no, we should keep all the trees. We should not put, let's say, solar panels in these areas. We should put them, you know, in the agricultural areas on the outskirts. May well be. But you know, you have to do the analysis, the study, to come up to that conclusion. So that involves really the economics of each alternative.
Probably the people doing the Green New Deal ideas are thinking about this already.
Possibly, yeah. But what we would like is to provide the tool to really implement these ideas, or at least test them.
Mm-hmm.
That's all.
Well, if there's no other questions or comments, again, I'd like to thank you for your presentation today. We're very happy you were able to do this with us. And
thank you.
applauding for everyone, right?
Okay.
Okay. I guess that's it, folks. We're done for today. See you in a month.
When is the next one?
Oh, I have it all written down, and of course, not on top.
Sorry about that.
It's the first Wednesday of next month. Let me get my calendar up.
Oh, November 4th?
November 4th.
Oh my.
I think it's Helen Feyervari from the Department of Germanic Studies speaking on Brecht and his friendship, I forget with whom, and she's a worldwide expert in this area.
Right.
Oh,
In fact,
great.
Helen's here. Helen, would you like to say something?
Sure, Julia.